Hey, Calc students, this is Mr. Beck. Today we're going to be talking about Taylor and MacLaurin polynomials. Now, what Taylor and MacLaurin polynomials are, is these are functions that we are going to turn into polynomials. So the Taylor-Maclaurin polynomial is the function that results that's going to model another function. So if we take a look at the screen to the right, in blue I have this graph of y equals cosine of x. What I'm going to do is I'm going to start turning this into a Taylor polynomial. To do that, I need to identify a point that's going to be easy for us to work with. 0, 1 kind of fits that bill. So I'm going to start by making, wrong button, I'm going to look at f of x equals 1, because that is our 0-degree polynomial at the y-axis. Now, if we want to turn this cosine into a polynomial, we had to have the point accurate, which is what we have. We also have to have the slope accurate, so we need to take the derivative. And we can see that the derivative at this point is 0. So, and the derivative of cosine is negative sine, and 0 is 0. So our linear polynomial is 1 plus 0x. That doesn't really do much, so I'm not going to hit enter. Now we need to turn this into a quadratic. To turn this into a quadratic, the idea is the concavity needs to be the same. So if the concavity needs to be the same, this should be a negative quadratic at that point. So I am going to type in negative x squared. And by typing in negative x squared, hit enter, you can see now I have a little bit better of a representation, but this isn't as accurate as what I would like it to be. So what I'm going to do is I'm going to go back to that equation and I'm going to make it wider. So if we add a horizontal dilation, or I guess a vertical dilation of 1/2, then we can see we now have a better representation of our cosine graph right around this point. So if I continue along with that, the next thing that we need is the same change in concavity. Since the point that we're looking at is at the top of the curve, there is absolutely no change in concavity there. So I'm going to skip over the 3rd degree and go to the 4th degree. So if this is a 4th degree polynomial, I take a look at this and say, this part of the polynomial looks like it's going to be opening up as opposed to opening down. So if I do plus x to the 4th, then, once again, I'm running into this idea that I don't think that this graph is wide enough. So what I'm going to do is I'm going to divide it by something to make it wider, probably a bigger number. Turns out that bigger number is 24. So if we divide by 24, now you can see that we are starting to model this part of the cosine graph very, very accurately. I'm going to go ahead and put in one more term, and then we'll see if we can guess what's going on. This is going to be minus x to the 6th power, and then divided by this number, 720. Now, at this point, if I show those numbers, some people are going, wait a second, I think I'm starting to see a pattern here, and that pattern is absolutely true. So you can see we're modeling the graph a little bit better. But if we take a look at the equation, what's happening, what's the relationship between these numbers? This is 2 factorial, this is 4 factorial, and this is 6 factorial. So we're going to build off of that as we go into our Taylor-Maclaurin polynomials. So I'm going to start off with this function f of x equals e to the negative x. And just like I did on the graph over there, I said, okay, we need to start at a point, f of 0 equals 1, which is what I have. Same slope, so I found f prime, and then f prime of 0 is negative 1. So now as I'm building my polynomial, that would be f of 0. This is f prime of 0. So we need our same concavity, which take the second derivative, and then f double prime of 0 does equal 1. If you remember, I divided by the factorial, so that would be 1 divided by 2 factorial. And keep going, f triple prime at 0. So that would be that value, and then divide by 3 factorial. If I keep going, you can already see the pattern of our derivatives, 1, negative 1, et cetera, 4 factorial. And I like to generalize the rule right now because that's going to be really important as we work in the next couple of sections also. So this is really going to be the sum from n equals 0 to infinity of negative 1 to the n times x to the n over n factorial. That's not going to be the highlight of this section right now, but it's good for us to kind of keep that in mind. Now, if we use the polynomial to estimate, and this is a 3rd degree Taylor polynomial, more specifically, it's MacLaurin because it's what we call centered at x equals 0. This 3rd degree polynomial at 0.2, you can see that I plug this into a calculator and I got that value. E to the negative 0.2 is that value rounded. So what we have is accuracy to 4 decimal places, or I guess 3 decimal places, but we're within 1/10,000, which is pretty amazing. just because we didn't have to do much work for our derivatives, and we got some pretty good accuracy there. In fact, this is how they came up with a lot of the trig values in terms of calculations. We allow computers to come up with those trig values by using polynomials. So, random fact of the day. The MacLaurin polynomial, as I mentioned, is centered at x equals 0. So we have the zeroth derivative, which is really just f of 0, divided, or f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared divided by 2 plus f triple prime of 0 times x cubed divided by 3 factorial, and we saw that was 6. And therefore, we can create any polynomial this way. What I would like to do is let's go ahead and go to the tab. Let's go ahead and type in the polynomials that we were just working with. I guess the function that we were working with was e to the, oops, don't need the control. Nope. So e to the negative x. That would be that function, and then the Taylor polynomial that I created, or the MacLaurin polynomial that I created, was 1 minus, let me scroll back up, 1 minus x plus x squared divided by 2, and then minus x to the third divided by 3. And I want one more, so plus x to the fourth divided by 4. So what we could see is right around here, that Taylor polynomial ends up being pretty accurate. So it's accurate within, I would say maybe about 1. You can see that the graphs kind of diverge from each other right here. So it's accurate within about 1. That's what we call a radius of convergence, and you'll hear us talking about that over the next couple of sections. But these graphs are virtually identical up till about 1 away. But anyway, that would be our MacLaurin polynomial centered at 0. So have a couple of examples. What I like to do is I like to just start listing all my derivatives. Feel free to use whatever like setup method works. So I like to show all of my derivatives right there. And by showing my derivatives, then I can plug in the value that I want. In this case, I want the x value of 0. So f of 0, f prime of 0, f double prime of 0, f triple prime of 0, 4th and 5th degree. When we go ahead and do that, and then plug it into our polynomial, we can see, or we set up our polynomial, I should plug in. So we have f of 0, which is 0, f prime of 0 is 1, f double prime is 0, f triple prime is 1, divided by 6. F to the fifth derivative of 0 is 1, divided by 5 factorial. What we can see is P5 of x is that. We can go ahead and type that into the calculator. I guess I'll probably skip over that right now just because we saw 2 examples already. One of the things that I like about this polynomial is, if you notice, all of the exponents are odd, and sine of x is an odd function, so it kind of matches up that the odd function would only have odd degrees. If we take a look at the cosine, which is what I showed on the calculator, all of those exponents were even exponents, and cosine is an even function. Example number 2a. So f of x equals cosine. Basically, this is what we did before. We did set up this 1 minus x squared over 2 plus x to the 4th over 24 minus x to the 6th over 720. I jumped. I probably should have looked a little bit at the bottom. What I did was I plugged in 0.2 for the Taylor polynomial and 0.25 for the Taylor polynomial. What you can see is a relationship between what our polynomial estimate is and our exact value estimate is. And it comes up with a very high degree of accuracy by not having to go out very far. So important for us to be able to look at, okay, what is our estimate compared to what is the actual result, or as close to the actual result as our calculator is giving us. And to have that degree of accuracy, it's important for us to be able to say what would our degree of accuracy would be. And we're going to get into that on the next page. So, also on the next page is, if we wanted to approximate e to the negative x at x equals 3, we would have a terrible approximation, because if you could see, e to the negative third power is right here, where our Taylor polynomial gave us a value that's way up here. So horrible representation. So in that case, we have to go ahead and recenter our graph. And if we recenter it at x equals c, the only thing that changes is we are now going to be shifting over our polynomial function to the right or to the left c, just based off whatever the c is. Now, also, it's going to be f of c, f prime of c, f double prime of c, f triple prime of c, et cetera, et cetera. So this is going to be important that we have Taylor polynomials centered somewhere other than 0, because what happens if we have, say, the natural log of 0? Natural log of 0, we all know, does not exist. It goes down to negative infinity. So we have to center it somewhere else. So we will center it at x equals 1. So let's go ahead and find f of x, f prime of x, f double prime of x. And I keep going further, further, further. Now I went to the fifth derivative here just to kind of prove a point. We plugged in 1 to all of those derivatives, which is what you see right here. When we do that, we have f of 1, which is 0, f prime of 1, which is 1, f double prime is negative 1, f triple prime is positive 2, fourth derivative, negative 6, fifth derivative, 24. Now in our denominators, we had 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial, which when we simplify creates this fifth degree Taylor polynomial centered at x equals 1. Now we can write this as the summation. That's not going to be the focus of today, but that's going to be pretty important. So with that said, or that's going to be pretty important for the future. So with that said, let's continue on. Our result from part A to approximate the natural log 1.2. So if I do that, I will get this decimal into my calculator. And then I want to know what's the difference between the actual and the approximation. So the difference between the actual and the approximation, we will take the absolute value of the actual minus the approximation. In this case, it was positive already. But anyway, we have a very, very high degree of accuracy. What happens if I want a higher degree of accuracy? Well, then I just build a higher degree Taylor polynomial. How would I know how far of the polynomial that I want to make in order to have a certain degree of accuracy? And that is where Taylor's theorem comes in, also known as the Lagrange theorem. So when it comes to Taylor's theorem, what we say is, okay, if we want a certain degree of accuracy, what would our bounding be? So the bounding of our accuracy is this formula, and I'm going to go ahead and zoom in. I need to do it slowly because the connection's not the strongest. So Taylor's theorem says it's going to be this expression. And I like to break this expression into two different components. First component is this absolute value of x minus c to the n plus 1 over n plus 1 factorial. Now, what I like to say is this is the coefficient of the next term. So our remainder at a certain term is going to be the coefficient of the next term times the maximum value that comes from the next term's derivative. So next derivative basically times the max change. So it's the coefficient of the next variable, or the next term, times the max change. And by looking at it that way, it makes more sense why this expression is the way that it is. So the coefficient of the next factorial, or next term, times the max value, that we do have this z in here that we throw in here, and this z throws some people off. Z is some number between x and c. So basically, what's the greatest amount of change from our polynomial? Like we did have cosine of x that we measured up to a certain point. If you remember, our graph kind of looked like that. So we want to know what's the maximum change between those 2 points, between the point that we have and the point that we're approximating. So with that said, what we're going to do is I like to do this a little bit more formulaic right at the beginning. So approximate cosine of 0.1. So with a fourth degree Taylor, I guess this is MacLaurin polynomial. I mean, really, MacLaurin polynomials are certain or specific cases of Taylor polynomials. So if I take my fourth Taylor polynomial for cosine, we've already written that down a couple times now. So fourth degree Taylor polynomial of cosine. If we plug in 0.1, we will get this decimal. I hope that you guys are trusting me on that one, just because it's going to save us time by just having that decimal there. I strongly encourage you to type it all in. I'm not going to, just because it's kind of tedious and keep the video as short as possible. So what is our remainder? Now, remember, what is our remainder? Our function value is going to be our polynomial plus a certain remainder. What that remainder is what we're trying to find the bound of. We know our remainder is less than or equal to the x, or really x minus 0. In this case, it's going to be 0.1 minus 0 to the n plus 1 over n plus 1 factorial times the max value of the rate of change of the next derivative. So 0.1, this, since we want a fourth degree Taylor polynomial, we're going to plug in 5. We need to find the max value of the, or the max amount of change of the next derivative. So let's go back up to the cosine one that we did. We said the fifth derivative of our cosine was negative sine of x. So what's the max value of the absolute value of negative sine of x from 0 to 0.1? That would be, if we think about the graph of sine of x, it's the absolute value of sine of x. So we know the graph looks like this. So our max value is going to be at the sine of 0.1. So using the calculator, we have 0.1 to the fifth over 5 factorial times the sine of 0.1, and we get this extremely small number. What that means is our cosine approximation is going to be the Taylor polynomial or MacLaurin polynomial approximate plus that remainder, or the polynomial approximation minus that remainder. And it's at this point, I have some people say, okay, Mr. Beck, I get the idea that we're trying to find the bound. If we're trying to find the bound of this, then and we're trying to do this without a calculator, we had to find the sine of 0.1 in the calculator, which is actually a very, very good problem, or at least a thing for us to look at. Say, okay, well, we had to use the calculator to come up with the approximation for not using the calculator. Doesn't really make sense. So what ends up happening quite often is we will look at what is that fifth degree, and we do know that the maximum value is at sine of 0.1, but we can go ahead and say, well, what happens, what's the maximum value of sine or cosine? This happens a lot with sine or cosine. That max value of sine or cosine is 1. So what that said is if we plug in 1 right here, so if we replace this with 1, we now get this expression, which doesn't really change our remainder that much. So a lot of times you'll see books just take sine and cosine and say, oh, whatever, the max value is 1. That's because you have to really do a lot more work to figure it out. And this is, I mean, I'm telling you, we have eight zeros there. So the degree of accuracy that we have without having to use the calculator to find the sine of 0.1 is perfectly fine. Last but not least is what I kind of hinted at earlier. What degree do we need of the polynomial do you need to estimate to have an error less than, in this case, 0.001? So if I want to estimate the natural log of 1.25, I like to write out my formula until I know it. So it's going to be less than or equal to the coefficient of the next term times the maximum value on that next term. So the coefficient of the next term is going to be, well, to do this, honestly, we just have to set up a t-chart. So our x value is 1 because we centered it at x equals 1. So we centered x equals 1. This is truly a Taylor polynomial. So 1 minus 1.25, the absolute value, that's 0.25 to the second power over 2. And the reason why it's the second power over 2 is because we're looking at the next term. I have that decimal approximation here. Now, what's the maximum value of that next derivative? The maximum value of that next derivative is going to be, well, which is bigger? And our next derivative is going to be negative 1 over x squared. So negative 1 over x squared. So I took the absolute value of that, compared the two, and I said, okay, that one's bigger. So 1 is going to be bigger. So our error is going to be the 0.03125 times 1. For our second term, we take the coefficient of the third term, which I have as the decimal approximation. Now, as we do our comparison between the two, so our derivative is now going to be 2 over x cubed, which is what I'm showing here, and compare them. 2 ends up being our winner. That's our max value. So 2 times all of that is 0.014. We're not within our 0.001, which is what we want. So we move on to the next term. So our third one, you can see I've highlighted it, which shows that that's going to be the answer. But to get it, 0.25 to the fourth over 4 factorial, which I have our decimal approximation here. Now our next derivative is going to be negative 6 over x to the fourth. So if I compare negative 6 over 1 to the fourth to negative 6 over 1.25 to the fourth, 6 wins. The absolute value of that, which is 6, that wins. So if we multiply 6 times that expression, we will get that, which is within the 0.001 that I want. So it takes a third-degree Taylor polynomial to be within 1/1000. Hope this was very helpful for you. I do have a sample AP problem at the bottom. I encourage you to do this one completely on your own. Just say, based off of the calculus that we know, could I solve this problem? To find your answers, this would be 2004 BC, question number 2. Now, back then we had 2 forms that they gave us, so I put number B. This is form B. So if you want to find the answer, go ahead and look at 2004 on the College Board website, which is AP Central. Now, this is my challenge for you. Can you do this? See what you can do. Good luck, Calc students.